Alright, in part 1 of the quantification videos, we discussed different types of amounts and their uses, namely moles, objective numbers, and masses. In part 2, we're going to get into contrasting amounts with concentrations, specifically moles with molarity. Now, in general, a concentration expresses an amount of some chemical per amount of volume of a larger mixture. And there are numerous types, but the one that you'll constantly hear about throughout general chemistry is molarity, which is defined as a mole per liter. We'll get more into these units momentarily. First, I just want to cover two things. First of all, molarity has several practical uses, only one of which I'm going to cover today, the rest in future videos as they become relevant. Another thing that I want to point out is that molarity is typically associated with something known as a solution, which is defined as a homogeneous mixture of one or more substances that are dissolved in another substance. So what does that mean? Well, let me define all of these terms with a quick example. Imagine we have some water and some salt. Now if I pour the salt in the water, what's going to happen? Well, we know it's going to dissolve, right? At least unless I pour the whole can in there. So let's confirm that really quick. Here's our salt, we're dissolving it. And because the salt is being dissolved, because it is the minor component of this mixture I'm making, it's what we call the solute. Whereas the water is the major component in the mixture and does the dissolving, so it's called the solvent. And the mixture, known as salt water at this point, is the solution. It's the combination of all of the components. We often deal with solutions in a chemistry lab, and I'm going to talk more about them in the next video. For now, let's keep our focus on molarity, which is defined as the moles of solute per liter of solution. For short, we would just call all of this capital M, which stands for molar. For our saltwater example, the top of this would represent the moles of table salt, which is really just NaCl, or sodium chloride, and liter of solution would represent the liters of the salt water that I had after everything was mixed together. So from here, I'd like to quickly contrast molarity with moles, and then get into a practical example of why we would want to use molarity for a calculation. Let's say that we have 4.00 moles of NaCl, i.e. salt, and they're dissolved in enough water to make a 4.00 liter solution. Well, the molarity of NaCl in that solution is found by just taking the moles of sodium chloride and dividing by the liters of solution, which gives us 1.00 molar, which means that you have 1.00 moles of NaCl per liter of solution. Now, sometimes the moles and molarities are directly related, and changing one changes the other to the same degree. For example, if I were to double the moles of salt in this solution, but the volume of solution is relatively unchanged. And that is a bit of an approximation. Adding more salt would definitely increase the volume of the overall solution a little bit, but in general chemistry, it's very common to neglect changes in volume caused by addition of more of the minor component solutes. And so we'll say that that volume stays at 4.00. When I divide 8 by 4, I get 2.00 molar. Notice that in this case, both moles and molarity have doubled, and it seems like they're pointlessly similar. But let me take a step back and show you how they can differ. What if this time, instead of increasing the NaCl in the solution, we double the water in the solution, thus doubling the volume? Note that since water is the solvent in the major component of the solution, adding more water is not a negligible change in volume. And in this case, the results are that our concentration changes as well. By doubling the volume that the NaCl is swimming in, we have halved the concentration, which we can see in the math. We take that 4.00 moles and divide by our new 8.00 liter volume. And so the molarity of NaCl in solution has been affected by this change in volume. However, the objective moles of NaCl have not changed at all. They're just more dispersed throughout the solution. It's this difference between moles and molarity that makes molarity an important concept for later calculations in general chemistry. The fact that molarity is sensitive to volume, whereas moles are not. So to quickly summarize, in the context of solutions, moles describe the objective amounts of solute, whereas molarity describes the amount of solute relative to the volume of solution. If you change the moles of a solute, but not the volume of solution, then moles and molarity will change in the same way. If you change the volume of solution, then moles and molarity do not change in the same way. Now, for a practical usage of molarity that we can immediately appreciate, let's recall from part 1 that we could learn how to make a product based on the masses of reactants, which could be weighed out. But weighing is something that's more appropriate for solid materials. While we can weigh out solutions, a much more appropriate measurement is volume. And using concentrations, we can do similar math as in part 1b to learn about how much solution we would need to make a product. So let's do a quick example. Let's say that we were to mix an HCl solution with an NaOH solution. When these two solutions meet, they will produce table salt and some more water. And if we were to heat our product up, wait, I already used that in the last video. Much better. If we were to heat our product up and evaporate all this water, we could generate some solid table salt. And let's say that I wanted 5.0 grams of our salt, and I have a solution of 0.25 molar HCl. And I want to know what volume of this HCl I'm going to need to generate this mass of sodium chloride. Using similar molar mass math as we saw in part 1b, we can find that 5.0 grams of sodium chloride corresponds to 0.085 little 6 moles of NaCl, where the answer should have 2 sig figs at the end, but because we're not done with the problem, I'm going to carry one extra digit before I do any final rounding. And to differentiate that extra digit from the true sig figs, I'm making it small. Now the mole ratio tells me that for every mole of NaCl that I want to make, I need to react an equal amount of moles of HCl. So at the start, I need 0.085 little 6 moles of HCl. So far, this is a lot like the example in part 1b, but here's where things changed. In part 1b, we next used the molar mass to translate moles of reactant needed to the mass of reactant needed. But since we're dealing with solution where volume is better, then at this point we're going to use molarity to translate moles into a volume, which can easily be measured. And so how do we do that? Well, we just remember what that molarity is really telling us. It's telling us that there are 0.25 moles of HCl per liter of solution. And notice how I've organized these units so that our initial moles will cancel and I'll be left with liters of solution. And when I do the math, I get 0.34 liters. And this volume can easily be measured. Now we could then do similar math with the NaOH provided we knew its concentration. So there you have it, differences between moles and molarity, and then a practical usage of molarity. Again, there are more reasons to focus on molarity in the future, but those reasons are a ways away. So that's enough for now.